Okay, guys, finishing up chapter 1, Science is Everywhere. Today we are going to do chapter 1, section 3, using the scientific method. So we've talked about what science is. Remember, science is a process that we use to answer questions. And then we talked about how we make observations. Really important to use all of our senses when we make observations. And now we're going to talk about when we answer those questions in science, what is the process that we use to answer those questions in science? It's important to do the same process all of the time because remember, we want to have things be repeatable because if I can repeat it, then I can prove it to be fact. So 1.3, using the scientific method. And I know this is not the first time you have heard of this. So when you look for steps of the scientific method, you can find in some places 8 different steps, 7 different steps. I forget right now how many steps your book uses, but overall the process is the same. So the first thing you're always going to do is you're going to make an observation or you're going to make an inference. Your textbook uses this example. So when Sam is kind of at the bus stop waiting for the bus, notices there's a spot on the grass where the grass looks brown. So Sam notices the grass is brown near the area where students wait for the bus. So the first step of the scientific method is making observations, just kind of noticing like before when I talked about notice that there wasn't as many bees at my garden during the year. That would be an observation. So make an observation or inference, first step of the scientific method. Second thing, I'm going to ask a question. So Sam asks the question, why is the grass brown near the area where the students wait for the bus? Asking a question. You make an observation, ask a question. Why is the grass brown? If I use my bee example again, why are there less bees in my garden than there was before? Then I'm going to make that educated guess. So I made observations, I asked a question, I'm going to make an educated guess. So Sam's going to make an educated guess, our hypothesis. He is going to guess students walk on the grass near the area where they wait for the bus. Remember, when we write a hypothesis, it's written as fact. We don't include I think. We do not include I think. It's just written as a factual statement. Remember, a hypothesis is an educated guess. So now let's think about what are we going to do next. I made the guess. What do? We are going to test it. So test it out. Perform your experiment. So test your hypothesis. So think about what Sam can do. So if Sam thinks maybe this is where the students walk by the bus, what do you think Sam can do? Maybe Sam, after school one day, can sit there and see, all right, I'm going to pay attention to how many students walk in that area. So when I'm testing my experiment, it's very important to collect data and you want to write it down. This isn't a time where you would in your head just go, well, I'm going to count and I'm going to try to remember. No, you're going to get out a piece of paper. You're going to get out an iPad, you're going to actually collect that data. Now, when we collect data, there's different types of data we can collect. If we collect data in the form of words, we call that qualitative data. So data in the forms of words is qualitative. Here are some examples of qualitative data. Let's say Sam just says students walk on the grass and the sidewalk. Maybe going off on some other experiments. Red and green apples are in a bowl. We caught a large fish. My dog ate his food. You notice those are all in the forms of words. I don't have any numbers attached to them. I'm just noticing something's happening. That is all qualitative data is, data in the form of words. If I collect data and it's in the form of numbers, we call that quantitative data. Look right in the word there, quantitative, quantity. If you have the quantity of something, if someone says, what is the quantity of socks you have in your drawer? Not that anyone's going to do that, but if they did, that would be the number of socks that you have in the drawer, not I have red and I have blue socks. No, how many red socks, how many blue socks do you have in your drawer? If we look at the examples from the previous page, if Sam actually counted, all right, 10 students walk on the grass, 3 students walk on the sidewalk. So there's a number. 4 apples are red, 5 apples are green. The fish was 5 kilograms. My dog ate 2 cans of food. So quantitative data is data in the form of numbers. So if you guys see numbers, quantity, quantitative data. When we perform experiments, we don't just write down quantitative or qualitative data all willy-nilly, loosey-goosey. You need to have it in tables. So beautiful lab data tables where that data is organized. You want to make sure that those results are reliable. And if they are in a data table, they are going to be much more reliable than just written down in random locations. If we can and the situation warrants it, then we take that data and put it into graphs. We love graphs. We're going to spend much more time on graphs in the next chapter. Graphs are pictures of data. They are wonderful. So instead of just seeing a number on a page, you see a picture of numbers. And most of us work in the world of pictures, and that's why we make graphs. So tables and graphs are going to be in the data section of your labs. Finally, after you collect your data, you make a graph if necessary. Now you're going to draw a conclusion. Remember, scientists don't have opinions. So this isn't an opinion section. You are stating, here's the data I collected. So you study the data and then you reach a conclusion. All right, what happened? Then you also say in your conclusion, does it support my hypothesis? My hypothesis is supported because, or my hypothesis is not supported because. Can you scientifically then explain your results? After this, sometimes too, then this will lead you to other questions. So after that conclusion, maybe it draws you back to the beginning, and that's part of the scientific process. We are always learning. That's why science textbooks, they don't last that long, because we are constantly learning new things as human beings so we can move on to the next part. So your textbook breaks it up into these 5 spots, these 5 things. It's probably the 5 simplest we can get it to, but this really is the process. Make observations, ask a question, state a hypothesis, collect data in an experiment, and then draw conclusions. That is the steps of the scientific method. If you follow that and you do what you're supposed to, your results are reliable. If you do not follow that step and you come up with results from something, they are not considered reliable, and we want those results to be reliable. So make sure when you guys are writing a hypothesis that it's a good hypothesis. So 2 other possible explanations for Sam's observations are, because remember, so he found that there was more people that walked in the grass. So then you could say it supported his hypothesis that the kids walk in the grass more. But a good scientist is always thinking even further and not just stopping there and saying, oh, yep, gotta be that, someone walked on the grass there. So the grass near the walkway is brown because maybe it's not getting enough water. Maybe that's another possible solution to why it's brown. Maybe the grass near the walkway is brown because it's not getting enough fertilizer. So scientists are always thinking more, thinking outside of the box, really trying to cover all your bases. You don't just, shut the door on it, because when we do that, we're kind of closing ourselves to opening up and learning even more information. Now, finally, we have to make sure we can test things. You can't just make a hypothesis out of thin air and not have the ability to test it. So a hypothesis has to also be testable. Anytime we write them, they got to be testable. If you can't test it, it's not a good hypothesis. We will often use lab reports in science for the scientific method, and you will notice when you do them, they will often follow right along those same steps of the scientific method that we just said. So follows the steps of the scientific method. And it's okay to have a hypothesis that's wrong. The scientific process isn't oh shoot, I didn't get my right answer. That's not it. You look at it and go, hey, all right, I learned something here. Let's go back to the drawing board. So even if you come to the conclusion that, wasn't the one you guessed in the beginning, that's okay, because any piece of information is leading you down the path to actually the right answer. So it's okay to get an incorrect hypothesis. Nothing wrong with that. So scientific laws are facts, are rules that describe an observed pattern in nature. So if we do the scientific method over and over and over again, and we find that something is true, we say it is a scientific law. We can prove it to be true. We can observe it. It happens all of the time. It is factual information. So the book says, can you think of a scientific fact about the sun or earth? So maybe we know when you drop something, it's going to fall to the earth. That is the scientific law of gravity. We know that to be true. It happens over and over again on Earth. Scientific theory, on the other hand, is a little bit different. Now, think of anything that's called a theory. When someone said, well, I have a theory about something, theory. All right, they have a theory, they're thinking it, they got all this evidence that it's probably true, but probably can't prove it quite yet. So scientific theories are explanations of observations or events. They're supported by observations and investigations, but a good way to think of them is we can't see them. They're really hard to see. So we deal with things that are really small and things that are really big in terms of theories a lot because they're kind of hard for us to see as human beings. And one of them is what you see on the slide here, the plate tectonic theory. So we believe that the Earth's outer crust is made of what we call tectonic plates, kind of like pieces of an eggshell on the outside of a hard-boiled egg. Our plates on Earth, same thing. Now, if I were in a satellite or if I'm in a space shuttle up in space, I can't see these. You don't see these things. But what we do know happens is these areas, like you see on the picture on the left here, lots of earthquakes, lots of volcanoes along those areas. So then when you start to use all of this evidence of things happening in those areas, is really strongly proving that we probably are right, but we just can't actually see them. So that's what a theory is. We've got all this evidence that it's there, we just can't see it, but it's pretty much accepted as fact because we have all this evidence that it occurred. All right, that is the end of chapter 1.